Welcome back, Mrs. Saunders here. Today, we're talking about simplifying radicals, and we're going to do this in two parts. I want to take it slow because simplifying radicals is so foundational to both algebra and geometry that I really want to make sure you understand what's going on here. So first of all, what's a radical? A radical expression is an expression with a square root. So this whole thing here, that's called a radical. The symbol, that little tent thing above the x, that's called the radical symbol. And then the x, or anything that's under the radical symbol, that's called the radicand. And with these radical expressions come some rules that we have to be aware of. Rule number 1, no perfect squares hiding under the radical symbol. So you'll see here 25 x squared 16 4. I've got them all just jumbled up under there, but that's just to show you that you cannot have those hiding underneath the radical. Rule number 2, no fractions in the radicand. And rule number 3, no radicals in the denominator of a fraction. In this video, we're going to just work through rule number 1, no perfect squares hiding under the radical symbol. So first of all, what is a perfect square? Well, I'll tell you. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5, 25. 6 times 6, 36. Those numbers on the right, 4, 9, 16, 25, 36, those are all perfect squares because they've been created by a number multiplied by itself. And here on the right, I'm going to put a list of perfect squares. So you can see all the numbers on the right that I have in red. Those are perfect squares, 4, 9, 16, 25, 36, 49, and so on. And all the numbers on the left in black are the numbers that created those perfect squares. So if I take a perfect square and put the radical on top, I'm saying the square root of 25, which gives me the number that created that perfect square. The square root of 49 would be 7. The square root of 121 would be 11. What happens, though, if you've got like the square root of 12? If I break 12 up into its factors of 4 times 3, I can see that there is a perfect square hiding under there, 4, and it can't be there. So I have to kick it out. And if I kick it out, well, I'm basically just taking the square root of it. The square root of 4 is 2. So to simplify the square root of 12, I get 2 root 3. Let's try the square root of 50. I could rewrite 50 as 25 times 2. 25 is a perfect square and it can't be in there, so I got to kick it out. I have to take the square root of 25, which is 5. So I have 5 radical 2. That 2 gets stuck on the inside. How about 108? Well, that's 36 times 3. Again, 36 is a perfect square. It can't be there. I take the square root of it and I get 6 root 3. Now, those were relatively simple because I could kind of see the factors in my head, but what if you can't see the perfect square hiding underneath? I'm going to show you how to do that too. So step 1 is to create a prime factorization tree and look for pairs of numbers at the bottom. A prime factorization tree is looking at all the possible prime numbers that get multiplied together to create a number. So the prime numbers, I'm going to highlight them here for you, 2, 3, 5, 7, and 11. There's more after that, but these are the ones you're going to see most commonly. So 153, well, what do I do with that? It's not divisible by 2 because it's an odd number, but if I take 153 and divide it by 3, I get the factors of 3 and 51. 3 is a prime number, so I'm going to keep that. 51, that breaks into factors of 3 and 17. So on the bottom, I have 3, 3, 17. If I multiply all those together, I get 153, but it's all prime numbers on the bottom. So I want to look for pairs of numbers. I got a pair of 3s right now, so if I bring my radical down, I'm going to write one number of each pair on the outside of the radical. So since I have a pair of 3s, I'm going to put a 3 on the outside of the radical. Numbers without pairs, well, they get stuck inside. So square root of 153 simplifies to 3 root 17. Let's try another one. 200. So first we're going to create the prime factorization tree. 200 is We could do 2 times 100. 2 is a prime number, so I'm going to keep that one. 100. Well, you have a lot of different options here, but when I see 100, I think 4 times 25. Now, neither 4 or 25 are prime numbers, so I'm going to keep going. The 2 is a prime number, I'll keep it. 4 breaks down to 2 times 2, and 25 is 5 times 5. Now that bottom row is all prime numbers. So I'm going to stop there, and I'm going to look for pairs. I have a pair of 2s, write one down. Have a pair of 5s, I'll write one of those down. And the 2 is stuck inside. What do I do with that 2 and 5 on the outside of the radical? Just multiply them back together again. So this ends up being 10 root 2. All right, why don't you try this one? Pause the video, give it a shot, see what you come up with. All right, how did you do? Well, here's one way you could have done it. 360 is 2 times 180. Keep the 2. 180 is 2 times 90. Keep the 2s. 90, 2 times 45. Keep the 2s. 45 is 5 times 9. Keep the 2s and the 5, those are all prime numbers, and 9 splits up into 3 times 3. Then we're going to look for pairs. So I've got a pair of 2s, stick one on the outside. Got a pair of 3s, stick one on the outside. And then the 2 and the 5 that are left, they get stuck underneath, and then multiply those together. So I end up with 6 root 10. Now, you might have looked at this and thought, what happens if I do 36 times 10? Well, if I take 36, I can break that into 6 times 6 and 10 into 2 times 5. So on the bottom, I have a pair and I have prime numbers. So here's a little trick. If you get to a point where you have pairs and prime numbers, you can actually just stop there. So I can take that 6, put it on the outside, and then the 2 and the 5 are stuck underneath, and I get the same answer, 6 root 10. That's just another way to think about it. Whatever works best for your brain is what you want to do. Now, what if there's a number outside the radical? See that 5 sitting out there? Well, we can deal with that. The inside, we're going to deal just the same, but let's keep track of the 5. So I'm going to bring that down. I put it in blue just so we can remember it. And then the 98, we're going to do what we've been doing before. That's 2 times 49. Keep the 5, keep the 2. The 49 breaks into 7 and 7. So I've got all prime numbers on the bottom, and that 5 stays on the outside. I've got a pair of 7s, so I'll write one of those down on the outside, and then the 2 gets stuck inside. And then multiply the 5 and the 7 together for 35 root 2. Okay, now, what if there are variables? Well, let's do a quick reminder here. What's x times x? X times x is x squared. That's a perfect square. So if I take the square root of it, I'll just get x back again. What's x squared times x? If I'm multiplying two things together that have the same base, I add their exponents. So let me put a little 1 right here so you can see that. So x squared times x to the 1 is x cubed. Well, what happens when I take the square root of x cubed? Well, I just showed you that the breakdown of that is x squared plus x, but see, we found out that x squared is a perfect square, so it can't be under the radical. So I have to kick it out, and it becomes the number or variable that created it. What's x to the third times x to the third? Well, that's x to the 6th, because 3 plus 3 is 6. So therefore, the square root of x to the 6th is x to the 3rd. Okay, what's x to the 4th times x to the 4th? Well, that's x to the 8th. So if I take the square root of x to the 8th, I get x to the 4th. So what you'll notice, if you keep doing this, is that variables with even exponents are perfect squares. So if you look here, so 6 is an even exponent. That's a perfect square. 8 is an even exponent. That's a perfect square. So what happens if you come up with something with an odd exponent? Let me show you this trick. I'm going to take x to the 9th and I'm going to split it into x times x to the 8th. So 1 plus 8 is 9, so I can do that. I'm going to keep the x, and then x to the 8, I can split that into x to the 4th times x to the 4th. So see, on the bottom there, I've got a pair. Each exponent is half, of the even exponent. 4 is half of 8. So now I can do what I've been doing before. One of the pairs goes outside, and whatever's left over is stuck inside. All right, let's do a couple more here. Lots of variables. So if you have x's and y's, you just kind of treat them separately and then smash them all back together in the end. So x to the 6th, that's x cubed times x cubed. And then the y, well, he's just stuck by himself. So again, I've got a pair of x cubed. I'll write 1 on the outside, and y gets stuck underneath. The next one's got, wow, numbers and letters. So the 25, 5 times 5. X to the 5th, I'm going to do that trick I showed you on the previous slide. I'm going to break that into x to the 4th times x to the 1. Y to the 7th, that also has an odd exponent, so I'll break that up into y to the 6th times y to the 1. All right, so let's keep the 5s. Those are prime numbers, and it's a pair. The x to the 4th, I can break into x squared times x squared. X to the 1, he's just got to stay there. Y to the 6th becomes 2y to the 3rds, and y to the 1 is just stuck. So it's getting kind of crowded here. But let's see what we've got. We've got a pair of 5s, pair of x squareds, pair of y cubed. So we'll put one of those on the outside, and then the little x and y, they're stuck inside. So that's simplifying radicals part 1. In part 2, we're going to cover the other 2 rules. But for now, thanks for being here.